students from AC graduate seminar. So for the first seminar, we have Dr. Ethan Ahn from the Department of Electrical and Computer Engineering, who is going to present on hardware implementation of machine learning by emerging nano devices. Dr. Ethan Ahn has been working on using nano devices for machine learning for the last 5 to 6 years or even more, even during his graduate days. And he has done some phenomenal work on kind of showcasing the benefits of these devices for hardware implementations. And he has a wide expertise in the design of these devices. And also he has brought in a unique expertise to UTSA in how to fabricate these nano devices right here. So it's our pleasure and honor to have Dr. Ahn with us today. He has received several awards and honors, including the Air Force grant in quantum electronic solids in 2019, the National Science Foundation Eager grant as well in 2019, and the John Bardeen Research Award for Excellence in Nano Device Research in 2014. And he also received the Best Summer Research Internship Award by T.C. Chen at IBM TJ Watson in 2013. And he's currently serving as an ECE Concentration Chair for Electronics, Materials, and Devices at UTSA. So if you're interested in electronics, materials, and devices, Dr. Ahn is the person to talk to. We are really looking forward to your talk today, Dr. Ahn. The floor is yours.
Okay, thank you, Dirisha. So does everyone hear me well in the screen, right?
Yes.
Okay, great. So good morning, everyone. Thank you for again joining today. So I'm gonna talk about this machine learning thing, but in a little bit different aspect of hardware. So today I'm gonna focus on, because I know a lot of audience today will be still graduate students. So I'm plan to provide you some enough information about motivation, introduction, stuff, so that it can be probably helpful for you to grasp some big picture in this area. So let's get started. All right. So introduction for neuromorphic computing. So basically, this neuromorphic computing, or in other words, bio-inspired computing. So this is basically a new computing initiative that is trying to take some inspiration from the way we actually compute. I mean, the human brain computes, because if we do this, then we expect we can actually increase the energy efficiency a lot, and also take advantage of what humans do actually, especially in terms of this machine learning tasks, such as image recognition, pattern classification, and all that. And for example, if you are given a picture of like a lot of people here, then we can actually recognize human faces here in just a fraction of a second, so almost immediately, right? So you can imagine how hard it will be, or how long it's going to take, for example, if we ask the computer to do this same job here. So obviously there are a lot of interesting features that we have, and the neuromorphic computing is basically trying to develop hardware that can mimic those functions here. So we already know that in this area of deep learning, we have been very successful actually, and we have a little bit of these features like all over our electronic devices, right? Phone, laptop, computer, and all that. And deep neural network actually means you have more than 3 neural layers here, and when it comes to its progress, we already had like a more than 96% accuracy in image classification, back in 2015, and even more. I think right now we are almost hitting 98% or 99% accuracy here in this job. So basically, in my opinion, Dick's great success in the field is probably a result, direct consequence of this lucky combination of three different parts. I mean, in order to keep making forward in this area, I think we need learning rules and some software algorithms, okay? And of course, because we need to train your machine, we need a massive set of data. And also when it comes to hardware, currently we are taking advantage of this GPU, okay? And because GPU should be much better than CPU, especially in terms of this parallel configuration, I mean, parallel computation. So because we have all these three triangles, that's why, you know, we've been very successful in, for example, you know, using and developing, you know, those artificial neural networks models, including, I think the CNN is the most popular one right now for image recognition, convolutional neural network. And there are some other kinds of models here too. So my topic, I mean, today is, you know, to look at a little bit more, I mean, what would be the future of our deep learning technology? I mean, even though we have been very successful, still there are many things that we can still do as a researcher. And the first question that we can probably ask is, you know, can we actually become more biologically inspired? Okay, so because a lot of current technologies right now, they are basically doing something called the supervised learning with labeled data set. But what humans actually do is
Ethan, we lost you there for a minute. Can you hear us, Ethan? Looks like Dr. An is facing technical difficulty. Just give it a minute. Looks like his internet connection dropped. Let's give him a couple more moments.
Hello?
Yeah, we can hear you, Ethan.
Looks like I got disconnected. Let's see.
No problem.
Let me share my screen again. So where did I?
You just were talking about the triangle, the 3 supervised and labeled data
Okay,
sets,
here.
right?
Right. Okay. Okay, not too bad. Right. Sorry for the inconvenience. Let's see. Yeah. So I was going to say just that our success has been due to the fact that we have all this triangle here. Okay. So in terms of we have this machine learning algorithms and also a massive set of data and also hardware. In terms of hardware, we have GPU that is actually better than, for example, CPU or any other computing units, especially in terms of parallel computation. And I like to say, even though we have been pretty successful so far, researchers are still looking into our future of deep learning, especially in these 2 different aspects, I believe. So the number one is, can you become more biologically inspired, for example? So because the humans can sometimes do also unsupervised learning without labeled data set. So in order to do that, we need the technology that is more biologically driven, biologically inspired. And the second one is GPU is, I think, advancing and making progress a lot in this area. But still, GPU, I mean, performance-wise, I think we are all good, okay. But power-wise, power consumption-wise, GPU is still consuming a lot of power. So maybe we should need have some other hardware platform that can actually replace GPU for improvement in power. So that's, I believe, the 2 research directions that we have right now for deep learning. And of course, non-volatile memory devices, we are gonna focus today. They can actually address this challenge very well. I mean, 2 of them actually very well. So before we talk about this, just I wanted to highlight that when it comes to power consumption, human brain is much better computing system than any other existing supercomputer in this modern world. And because we can do, for example, this board game with only 20 watt of power consumption, but see how much power should be consumed by the computer. Okay, so that's many orders of magnitude higher power consumption to the same job. And when it comes to why this is happening, this is because our human brain has these neurons and synapses. They are billions of them, and they are all connected and distributed in our human brain. So the key features are we can do massive parallelism, because again, these neurons and synapses are co-localized. It's not like our conventional computer where we have separate physical sections, right? That we have computing units, and we have other separate sections that we have memory units, and they're connected by bus. It's not like that. Okay? So they are all co-localized and distributed in our human brain, and that's why we can do these interesting things in a very power efficient manner. So in this area of neuromorphic computing, we actually aim to develop hardware, okay, that behaves the way the brain actually computes. So we are trying to see if we can actually make some artificial devices, okay, by electronics or some other technologies, but they have these synaptic functions and neuron functions, okay. So if you hear this, then you may ask, okay, is it really possible to create billions of hardware neurons and synapses, right? It's not 1 or 2 or 100,000, okay? So we need to make billions of them ultimately, and then also we want to integrate them into a microchip, okay? So you know what? Actually, this is not really surprisingly hard to do, because if you look at especially what we actually have done for the last like a half century, then in terms of this device density, we did actually really amazing job here. So for example, compared to 1960s, we only had 4 transistors in a a small chip, I mean, in a small coin-sized chip here. But right now, still, I mean, back in even 2016, the number of transistors went up all the way to billions. Okay, so see how many or how much improvement were here. And because we have this technology here, fabrication, nanomaterials, nano devices, so researchers are now looking into, hey, so let's look at, revisit this technology so that, we can develop high density, low power, neuromorphic, microchips. Okay, that's what we are trying to do eventually. And interestingly, when it comes to enabling devices technology, we have these nanoscale memory devices. Sometimes it's called a memristor. So I'm going to talk about this more in a minute. They already have successfully emulated a few biological functions already. Okay, so I think the chance is very, very likely, and because we have fundamental materials and devices technology, and we have this technique of developing a microchip. Okay, so let's just combine them. And when you say, we want to make artificial neurons and synapses, okay, so for example, for synapses, this is basically where, I mean, this is basically how this synapses work, very simply, and how we can make devices that can behave as synapses, for example. So the fundamental characteristic of synapse is actually memory. Okay, in this technology, sometimes it's called the plasticity, but basically they mean almost the same thing. So synapses basically behave as analog valves, okay, not digital valves. Okay, so here the important terminology here is analog. Okay, and that's how our brain works. And learning, memory, those are actually taking place actually in this synaptic component here. Okay, so neurons are more like a firing and sending and receiving, all these electrochemical signals. But when it comes to learning and memory, synapse is the place that all those things actually happen. Okay, and this is because we can actually update or tune these synaptic connections. So it can be even strength, and it can be even weak. How strong each neuron is connected, they can be actually modulated in a analog way, okay, in a grayscale way. So if you look at this neural network here, then the synapse is usually indicated by this weight. Okay, so when each neuron is connected to another neurons, okay, so how strongly they are connected. And what we are trying to do is, okay, so then can we use any devices, okay, or nanoscale technologies that can actually mimic, they can actually take this role of updating or tuning basically the conductivity. Okay, so that's what we want. So memristors are basically, it's a register, but it has memory. Okay, so that's why it's called memristor. Okay, so these are basically tunable nanoscale registers with memory. So with memory means, look at this curve simply. Okay, so when you say memory effect, then usually, when you have some physical characteristics such as IV curve and all that, you have to have some sort of what's called hysteresis. Okay, so hysteresis actually means what? So when you, for example, sweep your voltage, okay, in this direction, right, 1, 2, 3, and then if you sweep back 4, 5, 6, then you see a different curve. Okay, so going from one direction to another direction, and you're sweeping back to the original point, you don't get to the same curve. Okay, so you always get these different traces here, and that we call what we call hysteresis, and that's exactly what we mean by memory effect. Okay, so fundamentally, any excuse me, any new technology, any novel materials, novel devices. Okay, so if you find any hysteretic effect, something like this shown here, okay, so then that actually means, okay, so this device can be probably used as a synapse for neuromorphic computing, okay, because that means it has a memory effect. And again, here the important thing is it should be not digital but analog. So in terms of, for example, if you look at any device resistance or conductance, then you should be able to modulate in a gradual scale, not like 1 and 0, okay, not like a binary, but you should be able to get those numbers, values in resistance or conductance in a analog way, okay, so that it can be used to represent this weight, okay, or synapse or the connection strength between neurons, okay. Right, and I think one good example here is what's called a PCM, for example, okay, phase change memory, and I'm gonna talk this more about later, more in details, but here just I'm introducing this slide because this is part of the work that I got involved when I was doing PhD at Stanford, and what actually we show here is there is a learning rule called Hebbian theory, which is for sure biologically driven, and it is actually said to be neurons that fire together, wire together. So that means you have two neurons, like a pre-neurons and post-neurons, and when they fire the signal, like almost at the same timing, okay, so the signals are coming at exactly same timing, then the connection strength will be enhanced, okay? Otherwise, it will be loosened or it will be weakened. So the connection strength is really dependent on this relative timing, okay, between two neurons, and that's how we actually do, learning and memory and all that in biology. So then, and the research question here is, can you represent this by somehow, emerging memory devices or emerging nano devices? And yes, so here, for example, we have again this technology called PCM, and what's changing here is, you see here, we have this amorphous material region here, which is kind of dome shaped like this, okay, and all the background material is still the same material, but it's a different phase. So it's a crystalline material, so same material but in different phase, okay. So then because we know amorphous should be more resistive than crystalline, right? So your device current will flow, for example, something like this, okay, this is your current flow. So then your device conductance or resistance, okay, should be really tunable by controlling, for example, how big your amorphous region. Okay, so this is not, again, like a binary, okay, so it's very small, very large, it's not like that, but we can tune it like in a gradual way, okay, so small, little bit bigger, little bit bigger, little bit bigger, little bit bigger, something like that. And then the bigger amorphous region means you're gonna get higher resistance, okay, for example. So then, based on this technology, we were actually able to show, this again, a Hebbian learning rule to represent something called as TDP, spike timing dependent plasticity, and I believe this solid data here is real biological data, and this blue one is the one that we measure using these devices. And you see, overall, it actually represents the exactly same trend of this learning rule. Again, if you have this spike timing difference is almost 0, then you have your synaptic change maximized, okay? And if the timing is large, I mean, if they come at different timings, then your synaptic strength actually weakens, okay? So that can be exactly explained by this device technology, okay? So again, no need to worry about, too much details here for now, but if you are interested, feel free to look at this paper here. And just have the idea of, okay, so we have device technology, okay, already they can actually mimic some of the important biological functions that happen in our brain, okay, so that's the important thing here. And also, when it comes to this second challenge here, just I wanted to quickly highlight that, this non-volatile memory technology can actually address this challenge too, because if you look at how this neural computation actually works, for example, for CNN, convolutional neural network, then inside this, you have a lot of matrix vector multiplications, okay, between feature maps and filters. And this matrix vector multiplication is exactly what non-volatile memory does, okay, in this specific architecture called crossbar array. So you have these crossbar arrays in memory. Like sometimes you can call bit lines and word lines and all that. And then because we know your current, okay, so in one specific line is actually summation of, for example, voltage in each line here times the conductance in between. Okay, so it will be given by this equation here, and that this is exactly the matrix form of calculation. So because of this similarity, non-volatile memory can also be used very well to do this neuromorphic computation. Okay. All right, so I think that was pretty much for introduction, and I'm gonna do a little bit more presentation on this technology again. So we are looking at this emerging nano devices called non-volatile memory, right? And let's look into this a little bit more here. And because for the sake of time, I don't think I can give you like the whole thing of what's going on here in this field. So rather, I just plan to give you, what this technology is, and also some of the research activities that I'm doing here at UTSA. So I plan to, introduce to you about those things. Okay. So when it comes to memory, you probably already know this, right? So we have SRAM, DRAM, flash, right, in your computer right now, and they are basically charge-based transistors. Okay. And when it comes to new technology, I mean, emerging technology, so these are, I believe, the candidates that people like to research right now a lot. For example, we have this spintronics technology, STT-MRAM. It has magnetic thin films that are separated by some oxide. And, the speed information is actually represented by either, they are parallel, the magnetization direction is parallel or anti-parallel here. And we just talk about PCM a little bit, right? So the phase change memory here. And also we have RM. This is based on metal oxide thin film. And this is more like a capacitor. I mean, exactly capacitor, but I'm going to talk about this more later. And also, I just wanted to bring this technology called Airframe, ferroelectric random access memory. You know what? Airframe has a you may think, Airframe is not a new technology, because that's kind of true, because Airframe has a relatively long history, and it has been actually studied and developed like a while ago. But I think because of some like a device manufacturing issues and CMOS compatibility issues and all that, I think Airframe study and research has been kind of stopped for a while. So for maybe starting from I'd say early 2000 to 2010, I believe, there were very few people who actually look into this Airframe anymore, because that technology has been kind of considered as kind of died. Okay, but interestingly, right now, people actually started looking into this Airframe again, mainly because we recently discovered that this ferroelectricity. Usually, the ferroelectric property was a characteristic of some specific oxide materials, like a perovskite oxide, some complex oxide. Okay, and these complex oxides usually have some issues in CMOS integration. But right now in the field, very lately, researchers actually found this ferroelectric property in not only this complex oxide, but also some other oxides that have been conventionally used, and something that we feel familiar with, for example, Halfling Oxide. Okay, so Halfling Oxide has been used in CMOS a lot as high-K dielectric materials. Okay, so we know a lot of, we know well about this material, and we have a lot of knowledge about this material. So, but we found ferroelectric property there, okay, in those familiar type of materials. So that's why people are really looking at, okay, this ferroelectric technology for data storage, and also even for neuromorphic computing, I believe. So I'm not going to talk too much about ferroelectric RAM for today, but just be careful that this Airframe is also now becoming a major part of this research for neuromorphic computing. Okay. Right. So basically, for the remaining time, I plan to talk each technology here, RM, PCM, STTM, RAM, because those are the technology that I'm currently working on. So for RM, let's see here. This RM is basically the only technology that can actually potentially compete with 3D NAND for mass data storage applications. I think the other emerging memories, they can be fast, they can be energy efficient, they are all good. But when it comes to, it's really possible to do mass production and, came into reality, then, always this question of, how effective it is in terms of cost, right? So we have to think about this issue. And when it comes to this, RM is the best candidate here because you see here, it's very simple structure and it's easy to make, and the device physics and all that, they are all well known. So that's why people believe RM is very promising technology here. And of course, we are talking about neuromorphic computing right now, right? So for neuromorphic computing, still very promising because of its low cost feature and also seamless comparability. And also, like I said earlier, for any new technology to be used as, for example, Synapse, okay, so artificial synaptic device, then we need this capability to modulate conductance in a grayscale, okay, not in digital scale, okay, not 0 and 1. So RM can definitely do that. So that's why there are many research going on here using RM, metal oxide based RM as artificial synaptic element in neuromorphic computing. So let's talk RM a little bit more about here. This RM technology actually is dating back to 2008, I believe. And there was a actually very short but very seminal paper published at the time by a group of researchers in HP. And I believe this leading person is now a faculty member in Texas A&M right now. And this paper had this interesting title, "The Missing Memristor Found." Okay, and at the time it was very interesting, but no one actually knew what this is actually. I mean, what physical property it has, and how do we define and design this technology. So, but they found more in terms of like a circuit elements. Okay, so we have resistors, capacitors, inductors, and they like to make some symmetry between them. Okay, so if we have one technology here in place, then we need to have a pairing technology in other place and something like that. So based on this circuit elements, they found, okay, so there should be something that we don't know yet, but it looks like something is missing. All right, and they named it as memristor here. And later on, of course, there were many follow-up researches going on here. So right now we kind of understand, how it works. And also, we were able to, fabricate devices and, characterize devices and all that. So just briefly here, the RM is basically, working on this reversal transition, okay, between the low resistance state and high resistance state. And this transition actually happens because we can make your oxide kind of partially leaking. Okay, so we kind of damage your oxide purposely, but not to be permanently damaged. You know what I'm saying? So we kind of apply a voltage, okay, and then we create some leakage path here in your oxide. But again, this leakage, this damage is not permanent. Okay, so in a sense that it can be actually recovered, right? So once we have this leakage here, then because there's a leakage current path, so we can say your oxide is in low resistance state or high conductance state, right? And then we can apply a, for example, negative voltage back here, so that you can kind of recover part of it, right? So now your leakage is only here, but this top portion is fully recovered to a non-damaged oxide. Okay, so then you may not have high current here anymore. So then it can be a high resistance state or low conductance state. Okay, and you can go back and forth between them again by controlling this voltage. So in terms of this nature, we know this conductive filament is a actually oxygen vacancy, okay? Because we know if you apply positive voltage, then this metal oxide, okay? So metal, transition metal and oxide, okay? So, and oxygen ion is negatively charged. So oxygen ions will be pulled up, leaving behind some vacancies here. So that's why it's called oxygen vacancy. And we also know how to characterize these materials devices, and we get this hysteretic curve, right? So this is basically how you go back and forth, and you see certainly we have this memory effect here. All right. So here comes some specific research projects that I'm doing right now. So for neuromorphic computing, I'm actually looking into this aspect of variability. And you know what, actually, when you have these RM devices, these device parameters such as the resistance, you see here the resistance here, so they kind of fluctuate a lot. Okay, it's not like one flat line. They fluctuate a lot for different cycles here. So resistance, switching voltage, current, they all kind of changing. They all vary greatly in each programming cycle. Okay, so this is really not good for neuromorphic computing, because each conductance value, resistance value should be used to update your synaptic weight, right? But if this has this kind of huge variation, then how come we ensure your model is accurate enough? Okay, so it's going to significantly degrading your model accuracy here unless we solve this issue. So I'm doing some research to figure it out, what would be the physical origin for this variability by looking at where are actually these defects, because this defect can be a physical origin for this variability, and these defects can be either inside your metal oxide, okay, and they can be a stochastic nature for sure, like studied by some other groups also, but I'm more like looking into those defects actually at the interface. So the interface between top electrode and your metal oxide here. So because of the randomness that exists in this interface, so I believe that's why we have this large variability here. And I'm doing some research in, for example, how can we engineer this interface better, so that in each cycle we can have, for example, the same amount of oxygen vacancies and all that. So my idea is actually, unlike some other research groups who are trying to use some transition metal elements here, which can be easily oxidized, for example, titanium, tantalum, hafnium, aluminum. But I'm actually doing some research here to use 2D nanomaterials here, like graphene, actually to replace those metals. This research is still going on, and I think in order to talk about this, I think I have to give another 1 hour long or 2 hour long talk again. So rather than talking about this, I'm just highlighting why I'm doing this and what is the issue in this area, so that you can have a better idea on what's going on here. And also some other research that I'm doing, which is collaborating with my advisor at Stanford, actually includes making something called bi-directional modulation. So look at this IV curve here, okay? So, and like I said, one of the prerequisite for this new device to be used as a, for example, synapse, right, is the fact that they can do gradual modulation of conductance, right? So if you look at IV curve here, then usually when you do this set transition here, then you usually get this very abrupt transition here, okay? And if you go back to low conductance state here by reset, okay, so then it's more like a gradual, okay? So it's kind of asymmetric here at default, and this part should be, I mean, already suitable for neuromorphic computing, right? Because it's more like analog, and this is more like a digital, right? So we actually did some work here to see if we can actually tune this part also, okay, so that part also, so that it can be also a little bit more gradual, so that it can be actually bi-directional device that can have more room, okay, so more places to play with for neuromorphic computing again, all right? Okay, so I think I'm not disconnected or something, right? Okay, so just to make sure. All right.
No, you're good. We hear you.
Okay, just to make sure. Right. Yeah, because of this connection, I think I need to speed up a little bit here, but I think, yeah. So I'm gonna also talk to you a little bit about this PCM and also STTM RAM technology here, okay, a little bit. And so when it comes to PCM, phase change memory, this also has a relatively long history, which is dating back to 1960s. And because this phase change material has been, for example, used as a optical storage devices, all that. So it's kind of very mature technology, although we could still call them emerging or new, but among these emerging technologies, it is relatively mature. So that's good, right? And also PCM can also emulate synapses, because like I said earlier, by controlling the amount of amorphous region of your material, okay, so we can control the conductance in a gradual way. So that's good. So for those who are not familiar with this PCM, this is just a technology based on Joule heating, okay, and because there are some materials that can go back and forth between amorphous and polycrystalline state, and crystalline is low resistivity and amorphous is high resistivity, and this transition is actually made by again Joule heating. So you apply a current, okay, you apply electric current here, and then because your Joule heating will be I square R, right? So you're gonna generate some local heating in your material. So by this heat, they can actually go back and forth these two states. And this is some conventional device structure and some programming scheme, okay, that you have to apply some reset pulse and set pulse that is higher than some melting temperature of your material, crystallization temperature of your material, so that they can go to this phase transition here. So I think there are a lot of for example, review papers out there about using PCM as electronic synapse for neural computing, and I think I find this paper is one of them. And see here, for example, you can modulate your conductance, okay, in a gradual scale or in a gray scale. And for example, you can do this like to recognize this handwritten digit by using this PCM actually as artificial synapses in between here, okay? So, and also some research that I'm doing actually is more focusing on, the device fabrication and stuff. So you know what, again, our goal is not to make or 1 or 2 or 100, 1,000, right? So we have to ultimately make billions of them, billions of, I would say, synaptic devices, billions of neuron devices, okay, and then integrate them into microchips. So then obviously, there must be some fabrication and integration challenges for sure. And, individual devices then, should be at least, nanoscale, okay, even smaller than that. So, then there should be some certain issues that may arise because of this very small scale. And I did some study on, for example, when you actually do some dry etching, to make nanoscale devices, nanoscale PCM devices, then how does it impact actually your performance of your nanoscale PCM device here? So again, if you are interested, then feel free to read out this paper. I think that was published in a few years back here, 2019. All right, and the last candidate that I also wanted to briefly touch base on is actually spintronic devices, STTM RAM. So again, STTM RAM stands for spin transfer torque, magnetic random access memory. And you know what? In terms of performance, okay, in terms of, for example, switching speed, in terms of ability to achieve very, very low power consumption, STTM RAM is the best, in my opinion, okay? Even it can compete it can beat PCM, RM, and Airframe. Okay, so when it comes to performance, it's still the best candidate technology, but there should be some issues too, right? And I'm going to talk about that more later. And also another big advantage of this spintronics technology is it can actually emulate both synapse and neurons. Remember, when you talk about RM and PCM, I mentioned most times that RM can be a synapse, PCM can be synapse. Okay, so that's true, but it's very unlikely that you use RM as, for example, neurons, okay, or PCM as neurons, and that's why a lot of these neuromorphic chips that are developed right now, they usually combine this RM synapse or PCM synapse with CMOS neurons. Okay, so they still need conventional technology to make neurons. Okay, because the neurons should kind of generate some signals that are oscillating. Okay, and in order to make the signal oscillating, because this RM and PCM are basically register, right? So it's a kind of variable register, and that from maybe basic like a circuit courses, right? So in order to create a oscillating signal, then you need some capacitance or inductance, that kind of circuit elements, right? So that's why RM and PCM can be mostly used for synapse only, but this guy here, STT-MRAM, actually can do both. Okay, synapse and neuron. And furthermore, and this is, I think, the same thing here. So the spin devices, they can, excuse me, they can be used to store the data for sure as a memory, completely okay. And also it can emulate neurons, okay, because it basically can be used as an oscillator, okay, high frequency gigahertz oscillator here. So that's exactly what neurons do, okay. And even it can have this inner state, gray scale or gradual scale conductance modulation, so it can do that too. So that means it can be used as a synapse, okay. So tunability, okay, so it can be tuned to be used as a memory element. I mean the conventional type of storage element, or even synapse, neurons, they can be tuned very well. So that's really interesting and promising for spin technology here. And also, another important aspect of this is lifetime. Because we need to program this device and erase this device, and doing this over and over, right, until basically this machine finishes learning. Okay, and that means actually we are gonna again keep programming over and over, erasing over and over. So we need to use these devices for long time, okay, as long as possible. And actually that is related to this terminology called cyclability, or sometimes it's called endurance, right? So for this type of characteristic, spin devices are known to have much better endurance, cyclability, or lifetime compared to, for example, RM and PCM. Okay, so it was already demonstrated in 2016, for example, that this STT-MRAM device actually can be cycled, all the way to, for example, 10 to the 14 cycles. Okay, and I think the state-of-the-art RM and PCM, they can usually do up to maybe 10 to the 10 or 10 to the 12 cycles, but no more than that. Okay, so in terms of lifetime, also STT-MRAM has a very good promising aspect for neuromorphic computing. Okay, so based on this, this is one paper that I actually participated in here, and this is actually to develop a deep learning accelerating machine based on this spintronics technology. Okay, and I think in this work we work with our former faculty member, Dr. Duan. I think he is no longer with UTSA yet, but I work with him to basically provide my expertise in, for example, devices. Okay, so I think we were one of the very first groups who actually show that we can have these multiple resistance levels in one single spin devices here. And then, we developed some like a circuit level innovation and system level innovation, architecture level innovation. So that's why it's called the full stack framework. And because of this emerging spin technology, again, which is the fastest, which is the lowest power consumption, I think this deep learning accelerator featured very low power consumption than any state-of-the-art, hardware implementation of deep learning. All right, so I think, yeah, so it's 11:50 right now. So, so in summary, basically, okay, we need a better hardware platform, okay, that can possibly replace GPU, okay, because again, GPU is consuming a lot of power, and emerging nano devices. I mean, this non-volatile memory cannot be, may not be the only one technology here, okay, but I mean, there must be some other nano devices technology out there, but non-volatile memory is certainly one of them that is very promising, and they can help to implement neurons and synapses, okay. And because we have several candidates here, again, PCM, RM, STTM RAM, and also ferroelectric Airframe. So just the pros and cons is summarized here. Okay, so PCM is the most mature one, and RM is already having this low cost. Okay, that's good, but again, they can only emulate synapses. Okay, and STTM RAM, again, like I said, best performance, emulate synapse and neurons at the same time, but it has very high cost. Let me go back to some slides here. You know what? This is a material stack, okay, of conventional STTM RAM here. You see how many layers you need. I mean, you see how many materials you are using. Okay, top electrode, capping layer, free layer, MgO, and reference layer, ruthenium, cobalt, platinum, baryonic. So there are multiple layers, usually more than 10. Okay, usually you have to have more than 10 layers here that include magnetic materials, non-magnetic materials, and all different kinds of oxide materials. So there must be some challenge for sure in fabricating and integrating this technology for sure. Okay, so that's why. Although it has a lot of promising aspects, again, in terms of performance and in terms of emulating both synapse and neurons, but because of this high cost, still there are research and development more research and development efforts needed. But I think whenever I talk to this STTM RAM industry, looks like even this is now being tackled a lot. So they say, sometimes, they say, oh, the high cost is not a problem anymore for STTM RAM. We were able to, reduce the manufacturing cost significantly by, applying, some other, techniques and know-hows and all that they developed. But certainly compared to other technologies, I believe this is still the downside of STTM RAM. Right. Yeah, so I think that's pretty much it. So yeah, this is just acknowledgement. So for my students and some sponsors and collaborators, and that's it. So yeah, I'm gonna have some time for Q&A right now. If you have any questions.
Thank you, Ethan, so much for giving us a high-level overview on how these nano devices can help us build better hardware for neuromorphic systems or even traditional deep neural networks.
Yeah.
I think we have one question from the student, Fatima. You want to go ahead and ask?
Yeah, hi, Dr. Ram. Thank you for the beautiful talk. I was wondering, like in the last paper that you showed, the ICELIA work, how many levels of resistance was realized with the STTM RAM device?
Okay, so that's a good question. So the one that was used in that particular paper, we were actually able to get up to 4 different levels.
4 different levels. And did it impact the network performance? Because usually the weights in the neural network need a certain amount of precision. So 4 levels would mean 2 bits of precision. So
that's exactly right. Yeah. So yeah, because I mean, if we just look at the devices, then actually I could generate more actually resistance levels, but I found that those resistance levels are not very stable enough.
Mhm.
So yeah, the largest number that I can ensure, this is really programmable and reconfigurable and all that was actually 4. But like you said, 4 may not be really, sufficiently large enough for this purpose. So that's why, we added, some kind of circuit level, study too. For example, you can actually have one MTJ, one STM cell that has 2 bits multi-levels, and have another, for example, STM cell, and then you connect them in parallel, for example. So
Oh,
then,
yeah.
yeah,
Parallel
then you can
combination
actually,
multiple.
exactly. So you can create multiple combinations of these 2 devices so that you can increase the number of bits actually here. So that's actually what we did in this particular paper. But again, when it comes to how many energy levels, not energy levels, how many resistance levels you can create using STT-MRAM is actually still, not very high. So that's why still I'm working on it to actually improve the number. Yeah.
If I may ask a follow-up question, like how many did you need to parallelize, like for one synapse? Like you can combine multiple STT-MRAMs, I guess. So how many was good enough to get a stable performance in the
so
network?
one single synaptic weight, we actually used only 2. Yeah.
Okay.
And yeah, we found that it's actually actually our goal, if you read the paper, then I'm sure you know this, but our goal was actually to see by combining again these like architecture level and system level schemes, we wanted to see if we can minimize the number of bits required.
Oh, okay. That makes sense.
So
Yeah.
of course, it's possible that we increase this number of, for example, connections in parallel, so that we can increase the combinations and all the bits. But we actually studied. Okay, so let's say we are limited somehow. This number of devices and all that, or number of the training data, or that. So in that kind of limited situation, what best can you do? So for example, so yeah, that was actually the aim of this particular work. But just quickly for your question, we only used 2 devices actually for one synapse.
Thank you.
Yep. Yeah, I think that's a great question. Yeah. Any other questions at this moment?
As the students are trying to think through this, I have a few, Ethan. I think I'll try to keep it at a high level. I think you kind of mentioned the benefits of the different types of RAM devices,
Right.
in terms of low cost, or the ability to represent multiple states, both synapse and neuron, and so forth. Have there been any implementations where researchers have combined multiple of these devices to take the advantage of, that dual representation or modulation, and the low cost?
Yeah, so maybe you're asking about, for example, if we can combine, for example, RM or PCM as a synapse, and then STT-MRAM as neuron, something like that. Yeah, so yeah, definitely, and that's actually one of the research projects that I'm also thinking for my future research. And I think there are a few groups already, I think, who are doing this. I think the Royce group in Purdue, I talked to him, and it looks like he also has this idea there. There should be some few, but not many. But there are a few groups who already look into this direction. But yeah, I think that's something that we can try for sure. Yeah.
Okay, and the other specific question, perhaps in your RM operation, you have shown that this conductive filament is what helps in having this high resistance versus low resistance. Is there an understanding, at least in earlier days, I know there wasn't a clear understanding if it's a single conductive filament or if it's multiple conductive filaments that are being formed and destroyed? Is there a consensus on that right now as to how many filaments are formed with certain materials?
Actually, as far as I know, there's no consensus on that yet. Yeah, so yeah, still sometimes depending on the materials and device size, structure, or that sometimes we have single filament, sometimes we have multiple filament, and even they can come with a different shape, right? So yeah, so it can be single straight line or conical shape, So yeah, I don't think, we have any solid understanding on that yet.
Okay, I guess any other questions from students? Anyone else wants to ask? Please feel free to raise your hand or type in the chat. I guess one last question for you, Ethan. You mentioned something about 3D structures in the beginning. I was hoping to see a little bit more on that. Do you see any challenges in stacking this up in a 3D layer?
Oh, okay. So maybe you're the 3D RAM, you mean?
Yes,
3D
yes.
compared to 3D NAND, right?
Yes, so maybe in your case, you're talking about just a single RAM. I was thinking like a 3D crossbar of RAM. Is that what you talked about, the 3D RAM, or is it the device structure you're talking about?
No, I'm not talking about the device structure. So you're right. So I'm talking about the 3D architecture actually. And actually in 3D, actually there are two kinds. I mean, 3D, like you said, 3D crossbar, crossbar structure. And also there is 3D vertical, I'd say, structure. So yeah, what I meant is, I mean, this is like you have crossbar, the first layer, and then you add another crossbar layer on top, right? On top, something like that.
Right.
Yeah, so this should be something that is more intuitively easy to think of. And yeah, this 3D vertical is a little bit different. So this is actually the device itself actually has this vertical structure. It's not like you have thin films like that, but rather than that, it has oxide layer, for example, like in this kind of vertical structure, like a column shape. And then you have your electrode layer, for example, top electrode, bottom electrode, top electrode, bottom electrode, something like that. So it goes more like a vertical structure. So device-wise, it's completely different. Again, your resistive switching layer is not like this kind of planar thin film, but it's more like a vertical structure. So what I meant by this is this 3D vertical structure is actually the one that I believe the most promising in terms of increasing the density and lowering the fabrication cost. Yeah, because I know this 3D crossbar structure, I think Intel and maybe Micron and I think there are many companies are actually working here, but I hear that this is not really very well scalable to adding like more than 100 layers and 200 layers and all that. So
okay, that's great insight. Thank you so much. We'll probably follow up on that with you.
Yeah, sure.
Thank you so much for taking time and sharing this with our students today and our researchers in Matrix.
Yeah, no problem. Thank you. I hope it was helpful and enjoyable.
Yeah. Have a great
Thank
one.
you.
And see you all next Friday.